I'm here with David Anastasio with Santa Clara University. Can you go ahead and introduce yourself?
Sure. Hello, everyone. My name is David Anastasio. I'm a professor in computer science and engineering at Santa Clara University in the School of Engineering. And I'm here at the VDURA booth to talk about some of the AI work that we do in our lab. I'm going to present a couple of demos for a couple of the projects that are currently ongoing.
Great, thank you.
Yep.
So as you know, David, AI is transforming industries. Can you give us a little information as to how Santa Clara University is innovating in this space?
Sure. We have a number of faculty, not just in my own department of computer science and engineering, but in a lot of the other departments in the School of Engineering and even in some of the other colleges and schools at Santa Clara University, doing a lot of research related to AI. That is one. I also serve as the director of our HPC center on campus, and that is one of the most sought after commodity on campus, and that is GPUs. And everybody needs access to GPUs to train deep learning models for solving lots of interesting problems.
Great.
So the first demo I'm going to talk about is our work on hydrologic flow prediction. So we have been working with Valley Water, Santa Clara Valley Water Authority for the last 3 years or so, developing a number of models to predict stream flow and water reservoir levels 3 days ahead. So we want to know for any stream how it's going to perform in the next 3 days, how much water is going to go through it, and similarly for reservoirs, how full are they going to get, right? And that's obviously very important to prevent flooding, also for water management in general, to figure out whether we have enough water for irrigation and things like that. So we've developed a number of different models over the years, and today I'm going to talk about, or I'm going to give a demo of one such model called PF-Former. It's the latest paper that we published, and we're actually presenting that paper later this year in Australia. So without further ado, I'm going to play a video about our model called PF-Former.
Water is one of the most critical resources on our planet. Accurately predicting stream flow is essential for water resource management, flood prevention, and environmental conservation. In this project, we aim to predict the next 3 days of stream flow for 4 rivers in Santa Clara, California, using sensor data collected every 15 minutes, requiring a 288-step forecast. Our model uses as input a time series of past stream flow values and one or more associated time series, such as rainfall or stream flow from nearby streams. In this example, we can see real data from the Ross Creek in Santa Clara, California. The upper series shows the stream flow and the bottom one the rainfall values. We can see that the rise in stream flow is usually preceded by rainfall. In other words, these two sequences contain rich temporal relationships that are slightly misaligned in time. Another notable characteristic of these two sequences is observed in winter, which corresponds to California's rainy season. During this period, stream flow increases in sharp peaks, contrasting with the near-zero values during dry periods. Based on our observations, transformers struggle with time series data that contain infrequent yet crucial extreme values. In a traditional transformer model, positional embedding, or PE, is used to order values in a sequence. Each position is assigned a value based on a unique combination of sine and cosine functions at different frequencies. As an example, we show a 6-dimensional positional encoding that uses a gamma distribution to model sudden peak rises due to rainfall. The cyan line represents the original stream flow, while the red dashed line shows the stream flow after applying position embedding. As seen, position embedding introduces noise, causing key inflection points to shift and become exaggerated, potentially distorting the true temporal dependencies. We claim that informative multivariate signals can make position embedding unnecessary. Instead, our model uses cross-variable patches to naturally encode temporal dependencies more effectively. The PF-Former framework we proposed is a transformer-based variant optimized for multivariate time series forecasting. It replaces the encoder's positional encoding layer with enhanced feature-based embedding, or EFE, to capture complex intervariable relationships. For an input sequence of length t, taking the first time point as an example, EFE combines the predicted sequence value at this time point, corresponding values with auxiliary sequences, and S preceding values from each of these auxiliary sequences. The sequence is then transformed through a dense layer coupled with a nonlinear activation function. These elements are concatenated to form a multispatial subsequence unique to that time period. Adjacent inputs naturally have smaller distances when concatenated. In other words, they inherently preserve positional relationships. We use the hyperparameter S to control the concatenation length, allowing our model to adapt to more complex and longer sequences as necessary. In our experiments, we found PFFormer outperforms both the traditional transformer model and one without positional embedding, as well as many other state-of-the-art approaches in terms of root mean square error on 3-day-ahead rolling predictions across 4 different streams. Additional results can be found in our paper. We will now share some example predictions using PFFormer from 2 Santa Clara County waterways. The first animation shows streamflow prediction for the Upper Penitentia Creek, which is prone to flooding during times with unusual heavy rain. The graph displays predictions between December 8, 2021 and January 15, 2022, a period which included heavy rains. Every 4 hours, we predict the stream's flow rate in cubic feet per second for the following 3 days, shown here by the red prediction line. While most of the time the creek is dry, unexpected rain can cause the flow rate to increase drastically. Our model is able to stay ahead of these predictions, as shown by the green ground truth line that follows the red prediction line almost perfectly, in part with help from the rain gauge data shown in gray. We have slowed down the animation during the heavy rain period to allow closer inspection of the data. The second animation shows streamflow prediction for the San Francisquito Creek, another creek prone to flooding that has had considerable flood protection features added since 2016. We see that PFFormer is able to accurately predict ups and downs in streamflow along several extreme weather event periods. PFFormer is one of several streamflow and reservoir water level prediction models we have developed in recent years. Some of our hydrologic prediction models have been integrated into FlowView, a web-based monitoring platform that enables Valley Water to intuitively visualize predictions. FlowView automatically trains models based on user-selected parameters and generates 3-day-ahead forecasts, updating them every 4 hours. By providing timely and data-driven insights, FlowView supports Valley Water in making informed decisions for water resource management and planning. We would like to extend our gratitude to several of our partners in this project. First of all, Valley Water made the project possible by providing the data used for this research. VDURA is designing a parallel storage solution for the Santa Clara University High Performance Computing Center that will allow us to efficiently process large-scale data. Finally, we would like to thank Supermicro and NVIDIA for providing our lab with a high-performance GPU server equipped with NVIDIA HGX A100 8-way GPUs, which made the training of these models possible. These contributions have been instrumental in advancing this research and driving innovation in streamflow forecasting. This project is led by me, Professor David C. Anastasiou from the Department of Computer Science and Engineering at Santa Clara University School of Engineering, and is being developed by my PhD student Yanhong Li. Our paper, PFFormer, a position-free transformer variant for extreme adaptive multivariate time series forecasting, will be presented at the 29th Pacific Asia Conference on Knowledge Discovering and Data Mining, PAKDD, in Sydney, Australia this June. Thank you for watching our presentation.
Amazingly accurate in the predictions.
Yes.
So can you tell us a little bit about how this is important for the environment? Like, for example, the Coyote Creek flood came to mind and how catastrophic that was.
Exactly. So models like this are important exactly for that, so that Valley Water can find out ahead of time that a stream is likely to overflow its bounds and alert people that they need to move out of the way. Mm-hmm. One of these streams actually overflowed back in February this year, and unfortunately a number of apartments were flooded mm-hmm. because of it. But using tools like this, Valley Water can provide advanced warning to people so that they're not caught unawares and they can get out of the way of nature, mm-hmm. especially in this day and age with the kind of weather we're getting.
Right. Yep, agreed. Okay, and so the next demo is going to be about traffic analysis.
That's correct.
Okay, so tell us a little bit about what we're going to be watching.
Sure. So for this project, we've actually been working on a number of different traffic-related projects for the last 7 or 8 years. I'm also one of the organizers, along with folks from NVIDIA, of the AI City Challenge, which is this yearly competition where we spur on innovation in the area of video-based analytics, especially for traffic and a number of other smart city related projects. And so we've tackled problems such as predicting the speed of vehicles on the highway from just watching them through a video camera, counting the number of cars going in every direction at an intersection and classifying them based on whether they're a big semi or a smaller car, figuring out what drivers are doing. So the activity recognition, are they actually paying attention while driving or doing something else like talking on a cell phone, and all sorts of other problems. For this particular problem, we're developing models to describe what happens, especially when an incident occurs, such as a traffic accident, right? So again, these are very important for people, for us to understand what happened, as well as for us to very quickly, or for systems, very quickly identify what kind of response is needed, especially when an accident has occurred, right? So I'm going to play a little demo of a model that we're currently developing. Okay. So this one isn't done yet, it's not published yet, but this is ongoing work. It's a model we're developing that takes as input video camera footage or streaming video from cameras, and will describe in words all the different details of what's going on. Details about the car, about the environment, about the person or people, and things like that. Okay. And then we'll see, as part of the demo, a few different scenarios and some example descriptions that are generated by our model.
Okay, great.
Traffic safety is a growing concern, and AI is transforming how we analyze road incidents. Our project leverages multi-camera video analysis and AI-driven captioning to describe traffic incidents with high accuracy. With applications in accident prevention, insurance assessments, autonomous driving, and smart city planning, this technology enhances road safety, streamlines investigations, and supports urban mobility solutions. In this project, we use the Woven Traffic Safety, or WTS, dataset created by our partners at Woven by Toyota, which features accidents staged in a controlled environment with professional stunt drivers and pedestrians. To create an incident description, we begin by processing raw video footage captured from multiple viewpoints. To effectively analyze key moments, we extract 8 to 10 representative frames from each video. These frames contain crucial information about the scene, including pedestrian movement, vehicle motion, and environmental factors. Next, we introduce computer vision agents to extract meaningful attributes from each frame. These include pedestrian actions, such as walking, running, or being unaware, appearance details like clothing color and type, vehicle attributes including speed and trajectory, and environmental conditions such as daylight or nighttime settings. These extracted features serve as crucial contextual elements, helping ensure that the description being created is not only complete, but also factually accurate. They will be provided as a structured prompt to a visual language model, or VLM, to ensure that the model generates precise and context-aware captions, improving the accuracy and reliability of traffic scene descriptions. Armed with a structured site information, the VLM then generates accurate and coherent captions for each phase of the traffic scenario. This step allows us to create precise descriptions of pedestrian-vehicle interactions and finally describe if a collision occurred or was avoided. The result is a detailed, time-aware captioning system capable of describing normal traffic scenes and pre-accident moments with high accuracy. Next, we will show several examples of long fine-grained video captioning of traffic safety scenarios, including some involving pedestrian accidents. In this example, we observe multiple pedestrians navigating the scene. Some elements, like umbrellas, provide obstruction and add to the complexity of the scene. A woman riding a bike in a busy street is closely approached by a car, highlighting a potential hazard. Here, a biker moves forward, but a collision occurs as a car turns directly into his trajectory. Our model effectively handles nighttime events like this, generating accurate and detailed captions even in low light conditions. This scene captures an evening setting with deep shadows where a bike collision takes place. Our model prevails even in the face of visibility challenges. The agentic approach our method employs is primarily responsible for improvements in description accuracy. Here, we show two captions generated with and without vision agents. The description on the right, created without the aid of vision agents, is misleading in some cases and lacks critical details. The one created by our model on the left provides clear, precise, and contextually aware information, providing higher accuracy in describing the traffic scenarios. We would like to extend our gratitude to several of our partners in this project. First of all, Woven by Toyota made the project possible by providing the WTS dataset. VDURA is designing a parallel storage solution for the Santa Clara University High Performance Computing Center that will allow us to efficiently process large-scale data. Finally, we would like to thank Supermicro and NVIDIA for providing our lab with a high-performance GPU server equipped with NVIDIA HGX A100 8-way GPUs, which made the training of these models possible. Their contributions have been instrumental in advancing this research and driving innovation in traffic safety analysis. This project is led by me, Professor David C. Anastasiou from the Department of Computer Science and Engineering at Santa Clara University School of Engineering, and is being developed by my PhD students Ridham Kachadia and Danishta Patil. The Traffic Safety Description and Analysis task has been introduced as Track 2 of the AICD Challenge in 2024 and will be renewed in this year's version of the challenge, which is slated to start in April 2025. Thank you for watching our presentation.
So the city will use this data, or might be looking to use this data to improve traffic safety, but I'm thinking even insurance companies, but vehicle manufacturers.
These types of models could be used by city officials, departments of transportation officials, either at the city or county or state level, insurance agents, or just even to integrate other agentic flows. So, for example, we want to detect accidents and send out police or fire, to respond to the situation as quickly as possible, it would be useful to send them additional details.
Right.
Without having to send the entire video, we could very quickly send out a description of what happened and the details so that they can come prepared with the right equipment, right? And things like that. So, yeah, we're doing the research. We don't yet have someone that is likely going to use it per se, but we do basic research in our lab, and we hope that someone will use these models in the future for all
sure.
of these needs.
Yeah, it's very important work.
Yes.
Great. Okay, so last question. What role does high performance storage like VDURA play in making these AI models more effective?
Right. So, as you can see, these models use, especially these ones, use for this project, they use a lot of video footage, right? That involves thousands upon thousands of frames of video from lots of different videos. And when we train these models, we train them on many, many, many different scenarios with many, many, many different videos. So training these things takes a lot of data flow that is needed for the model to learn the right weights. And for that, we need storage that is capable enough to do that, right? So the VDURA solution is going to provide us with a parallel file storage system that is capable of reading up to 30 gigabytes per second, and thus able to process many videos at the same time. Our other project also uses data from the last 20 to 30 years of stream flow for multiple time series at the same time. So again, we need high performance storage to be able to train these models very, very fast.
Okay, great. Well, thank you, David. This has been amazing. Appreciate you taking the time.
My pleasure.